Good morning, guys. Today we are going to make a little comprehensive review about this idea behind the physical pendulum and the whole aspect that I want you to show is that if you have any kind of theory in physics, it is always possible, or it should always be possible, to make a simple prediction that you should be able to corroborate by experiment. So let's start by the physical and mathematical model and see how we can bring this down to something that can be corroborated, okay? Let's remember that your physical pendulum should be some kind of extended mass, some shape that you are trying to make oscillate around a certain equilibrium position. For example, if your physical pendulum is like this, let's say a uniform long rod of mass m, length L, because it is uniform, we know that the linear density is constant throughout the object, and you have it fixed in a frictionless situation or nearly frictionless around a pivot point, let's call it P. Then this thing is going to stay in an equilibrium position at a vertical. But if you pull it outward a certain angle from the vertical, it will experience a restoring torque. Well, a good approximation is that the weight mg of the object is going to act on the center of mass, and because this is uniform, the center of mass should be some distance d over here, and therefore you know that your net torque is caused by the fact that this mg is not acting on the pivot, and it is actually trying to accelerate the object back to its equilibrium position. So according to the right hand rule, this thing has a radius over here in red, a force over here. Your torque is negative. Negative distance d, force Fg, sine of your angle, which is basically the vector product or cross product of the radius and the force. Now, according to Newton's second law, in its rotational form, the net torque is also equal to the moment of inertia about the pivot point. Be careful with that. The moment of inertia has to be about point P times the angular acceleration. Now you can move over this term over here and change the elements a little bit. We know that the gravitational force is mass times gravitational acceleration times d times the sine of the angle. Now, if you wish to solve this in any meaningful situation, you need to change it to a differential equation. And so, the acceleration is the second derivative of angular position relative to the time, d2t dt squared, plus mgd divided by the moment of inertia about the pivot point, sine of the angle. Now, we have said before that this equation is extremely complex to solve when you deal with the sine of an angle. But if you consider that your angle is relatively small, say between 0 and 15 degrees, then it is a very good approximation, the famous small angle approximation, that for these small angles, theta is approximately equal to the sine of theta. And so your differential equation changes to the second derivative of position relative to times plus mgd over the moment of inertia theta equal to 0, which is one step away from the standard form of your harmonic equation, second derivative plus omega squared theta. Now, this of course means that you need to take your omega squared as the ratio mass of the object gravitational acceleration, distance from the pivot point to the center of mass, divided by the moment of inertia about the pivot point. We want to do this specifically, so we want to take into consideration here the length L of the rod and the moment of inertia of this rod about one endpoint. So if you take that, then your omega squared changes to mass times gravitational acceleration. Because the rod is considered to be uniform, then the center of mass should be at the midpoint. And so this distance in red, d, is L over 2, the length of the rod divided by 2. And then, according to previous calculations and tables, we have that the moment of inertia of a rod about one endpoint is 1/3 mass length squared. Of course, this simplifies things a little bit because the mass doesn't have to be taken into consideration, which means that as long as two rods are of equal length, they will have equal omega and equal period independent of their weight. Then also you see that there is an L or length here and there are two over here, so one of them is left. And so your omega is equal to the square root, switching things around a little, 3 times gravitational acceleration over 2 times the length of the rod. Now, if that's your omega, that means that your period should be 2 pi divided by omega, which is 2 pi square root of the reciprocal of omega, which is twice L over 3g. Now, this is what we want to check. We want to check that you actually get the period that you're supposed to. So I have here a little rod, or as close an approximation of it as I can get. This is a meter stick. It is equal to 1 meter plus or minus 1%, depending on age and tear and wear and tear. And so if you consider that your length is approximately to the nearest hundredth 1 meter, and g is to the nearest hundredth 9.81 meters per second squared, then it is a simple calculation that your period, 2 pi square root of twice the length over 3g, gives you a value of 1.638 seconds. Now, that's not very easy to check, but you can calculate the frequency, which is the exact reciprocal of the period. And so, because the frequency is the reciprocal of the period, your frequency turns out to be 0.6105 hertz, or more meaningfully, cycles per second. Now, that once again is not very easy to calculate or to corroborate, but you can also take the number of cycles per minute, and that's a lot simpler. Your frequency in cycles per minute will be 0.6105 over second times 60 seconds in 1 minute, which gives you a grand total with 3 significant figures of 36.6 cycles per minute. Now that's considerably easier to check. We can actually take this, and I have my stopwatch over here in the video. Let's start at the 10-minute mark exactly, and then we'll count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. And so that's a simple corroboration. We take a model, the model of simple harmonic motion that is governed by this equation. We make basic measurements and make a corroborating prediction, and we check that prediction. And that is physics for you. Thank you very much for listening. I'll see you later.